right now, my parents are drinking coffee. Coffee is hot. That cute girl that you like is also hot. But what's the hottest thing in the entire universe? We know there's an absolute zero, but is there an absolute hot? A point where something is so hot it can't physically get hotter. Well, let's find out. Let's start simple. The temperature of your body. The temperature of your body is not consistent. 37 degrees, 37 degrees Celsius, 98.6 degrees Fahrenheit. Sure, but those are averages. Your body fluctuates or increases by about 1 degree Fahrenheit or half a degree Celsius throughout the day in a cycle. At 4:30 a.m., your body reaches its coolest temperature, and at 7 p.m. it reaches its highest. But a bad fever is never good. 42 degrees Celsius is almost certainly lethal. The hottest temperatures on Earth happen 4 times in Death Valley, the hottest place on Earth. Temperatures there reached up to 54 degrees Celsius. At 82 degrees Celsius, that is the temperature needed for water when brewing coffee. And at 99 degrees Celsius, a cake is done. 1,900 degrees Celsius is the temperature of lava straight out of the ground. What about our sun? It's very hot. How hot? Well, its surface is 5,500 degrees Celsius. But the inside is even more insane. Temperatures at its core reaches 15 million degrees Celsius or 15 million Kelvin. For context, the Kelvin scale uses the same units as the Celsius scale, but it's an absolute scale, a scale where 0 Kelvin equals absolute 0. At this temperature, matter emits energy, radiates energy off of the object. And that causes it to be hotter. If you were to light up the head of a pin to the temperature of the inside the sun, it will kill anyone within a 1,000 mile radius. The energy an object emits tells us how hot it can be. Anything above absolute 0 emits some sort of electromagnetic radiation. We don't emit visible light, but we do emit infrared light, a type of wavelength. This is where light is so redshifted that we can't see it. Infrared cameras can though, like the James Webb Space Telescope, JWST for short. It uses an infrared camera. We can also see how hot a object is by looking at its wavelength. Cooler things have a bigger wavelength, and hotter things have a shorter wavelength. It starts with radio waves, microwaves, infrared, ultraviolet, up until X-rays and gamma rays, which are formed in the middle of our sun. Now temperatures at temperatures like the inside of our sun, matter exists in a fourth state. Not solid, not liquid, but gas, but something else. For context, this is an atom. This is not how an atom usually looks, so we're simplifying it. The things with the plus icon are called protons. They emit positive charge. The The things with the minus mark are called electrons. They emit negative charge. The circle, the unnamed circle, is called the neutron, as you can see. And the whole area of the each side of the protons and neutrons where the electrons orbit is called the nucleus. But anyways, at temperatures this high, matter exists in a fourth state where the fundamental particles of an atom, the protons, neutrons, and electrons, wander away from the nucleus. We call this plasma. Remember this for later. Now, temperatures at the center of our sun are already very impressive, but a star 8 times bigger than our sun, on the last day of its life, when it collapses in on itself, it forms temperatures of 3 billion Kelvin, or 3 gigakelvin. But let's get hotter. At 1 terakelvin, 1 trillion Kelvin, things get weird. Remember plasma? But that's not the... Well, at 1 terakelvin, the protons, neutrons, and electrons melt into quarks and gluons, smaller particles within protons, neutrons, and electrons and atoms themselves. But how hot is a terakelvin? Frightfully hot. There's a star called WR104 located 8,000 light years away. For context, a light year is a form of measurement. It's how long it takes for light to travel. So if something is 1 light year away, that means it takes light 1 year to travel. It takes the light from that object 1 year to get to us. But anyways, WR104's mass is about 25 of our suns. And when it dies, the gamma radiation within gets so intense it flings out into space and produces more energy in a few seconds than the sun will produce energy in an entire 10 billion year lifespan. This is called a gamma ray burst. They usually form when a black hole is born upon the collapse of very big stars. Gamma ray bursts are pretty narrow, so Earth is pretty safe. But what if it wasn't? Well, WR104, even though it's located 8,000 light years away, the energy it emits will still be bad news to us. Exposure for 10 seconds means losing 1/3 of Earth's ozone layer, leading to mass extinction and starvation. Back on Earth at Switzerland, scientists in labs were able to make temperatures around the 2 to 13 exakelvin or 1 quintillion Kelvin range. But don't worry, we're safe, because these temperatures only last a very short time because they only require a few particles. But now, the limit. The absolute hot. Remember how I said we can calculate how hot an object is by calculating the length of its wavelengths? Well, if an object reaches 1.41 times 10 to the 32 Kelvin, or 141 nontillion Kelvin, it will have a wavelength of 1.616 times 10 to the minus 26 nanometers, which is tiny. As I said, it's tiny. So tiny that it even has a special name, the Planck length. The shortest distance or length allowed in our universe, 10 to the minus 35 meters. But what if we just keep adding temperature? Shouldn't the wavelength get smaller? It's supposed to. This is where we got a problem. Anything above 1.41 times 10 to the 32 Kelvin, the Planck temperature is very hot. Hotter than temperature. It's so hot that what it is can't be considered temperature. Now, Now, if an object ever reaches that heat, it will collapse in on itself and form a black hole. Black holes like this have a special name, a Kugelblitz. So, in summary, the 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 highest temperature allowed in our universe is 1.41 times 10 to the 32 Kelvin, or 141 nontillion Kelvin. Luckily, we don't know of anything that has that temperature. So this is all possible, though this is all kind of a theory. But anyways, I hope you learned something, and thanks for watching.